Hi everyone, so my name is Ashley, and today I'm going to show you how to solve a combined spectral problem. And this is the formula we're given, C7H14O2. This is the IR spectra, the CNMR spectra, and then the HNMR spectra. But first we want to determine the ratio of carbon bound to hydrogen, which would help to determine if we have a structure like a ring or if we have any pi bonds. And then each pair of hydrogen missing from the formula indicates those things. We also take into consideration the presence of halogens or nitrogens, but since there aren't any in this formula, we're not going to worry about that. And then oxygen does not alter this the way that those do. So the formula is 2n plus 2, with n being the number of carbons. So 2 times 7 is 14, plus 2 is 16. And then we subtract the number of hydrogens we have, which is 14, so 16 minus 14 is 2. And then we divide by 2, so 2 divided by 2 is 1. So this is telling me that there is a pi bond somewhere in this molecule. And then looking at this, this is the infrared spectra, and it gives us an idea about the functional groups we have, and we can compare it to the formula we're giving. So if we look between 2500 and 2000, this is the triple bond region, and I'm not seeing anything there, so there are no triple bonds. And then between about 2000 and 1500 is the double bond region, and we have this one long peak here, and it's at about 1700, which would tell me that this is probably a carbon double bound to oxygen. And then we have this peak here at about just before 3000. And this is the area where we would find sp3 carbon bound to hydrogen. So we're looking at some kind of an alkane with a carbonyl. And then if we look over here, we can rule out any OH groups because there would be a big broad peak right here. So don't see that. And then everything below 1500 is considered the fingerprint region, and it doesn't give us much input on functional groups for the molecule. So we're going to ignore all of these peaks to the right here. So going down, this is the HNMR spectra, and it tells us the number of signals, which signals are the groups of unique protons in a molecule or the number of unique carbons bound to hydrogen. And this is important to remember that this considers symmetry within the structure of the molecule, and I'll explain a little bit of that in just a second. But looking at this, we have 5 unique signals. So 1, 2, 3, 4, 5. So knowing this is helpful because when we are given the formula, it says that we have 7 carbons. And that means that there's going to be some kind of an identical group, such as 2 methyl groups bound to a carbon. Or, this also affirms that our idea that there's a carbonyl, which would not have any hydrogens attached to it because of the double bond. And therefore, it wouldn't be represented in this particular graph. So some orientation here. This x-axis, displayed in parts per million, it shows the chemical shift, which represents how shielded a nucleus is in a molecule and the overall difference of frequency between groups. And the word spin refers to the multiplicity, which is the number of peaks in each signal. So if you look at here, right around 4 parts per million, we have 4 distinct peaks within this one signal. And this refers to how many neighbors each group of hydrogen has. So this refers to how many hydrogens are attached to the next carbon on either side of the carbon, represented by that particular signal. and we use the formula n+1, or neighbors plus 1, to determine how many peaks will be shown. So I'm just going to pull up what I believe this structure is so I can show you guys exactly what I'm talking about here. So if we look, this group of hydrogens and this group of hydrogens here are identical. They're attached to this carbon, and then they're 2 carbons away from this double bond of oxygen. So this would be one signal. And then we have the second signal here, third, fourth, and then that would be number 5, which corresponds to the 5 signals that we saw in the graph. So let's look at these hydrogens in particular as an example to show you how it would be represented on the graph. So they have one neighbor here, one hydrogen, n+1 is 2, so it would be a doublet on the graph. Right here. There's also a doublet here, but if you look how tall this is, this would represent the 6 hydrogens, which is the integration. It just means the number of hydrogens in that group. So this would be a 6H, and then it has one neighbor plus 1, so a doublet, 2 peaks. And then we can also look at the CNMR spectrum, and we see 6 signals. 1, 2, 3, 4, 5, 6. And we're given a formula with 7 carbons. So what's the difference there? Well, if you remember, these carbons bound to hydrogen are identical. So we can count those. This one and this one are the same signal. So 1, 2, 3, and then we're counting this one, even though it's not bound to hydrogen. For the CNMR it counts 4, 5, 6. And also, if we take a look at what's going on right here, you'll see the farther downfield, so if you're looking, this would be upfield over here, this would be downfield. The farther downfield a signal is, means the closer that it is to a more electronegative atom. So that carbon would be at around 172, and that would be the carbonyl carbon, because it's closest here to this oxygen and that oxygen. And each of these numbers corresponding to how close they would be to that double bound oxygen are displayed here. And then I just wanted to add one more thing that I also used for how I determined where to put this carbonyl in. So this is an ester, obviously. You want to take a look at whether there are any single peaks here, because that would mean no neighbors, right? That would be 0 plus 1, so a singlet. And I'm not seeing any of those here. So that told me that there wouldn't be a lone methyl group on either end of this molecule, because if it was just this methyl group right here, and then this CH2 wasn't here, it was just this carbon bound to this oxygen, that would be a singlet, and I didn't see that. So that's how I knew that we had groups on either side of the carbonyl. And that was how I pieced together this molecule. And I hope that you found it helpful.